All right. So let me just fix this. Okay. So I hope you can see my screen. I am going to go over the highlight of this problem again in a similar way to what I did with the other section, and maybe this is gonna sound a little bit repetitive, but quickly will um, like consolidate the whole procedure in your mind. I hope so. So basically, in this problem, based on what was given to us, these are the information. Just to remind you, we want a reliability of zero point 0.9. The pinion has a life of 10 to the power 8. The hardness for the pinion was given to us, as well as the hardness for the gear. And we were told that these are grade 1, both of them. This is a spur gear with a pressure angle of 20. J, the geometry factor for both were given. The number of teeth are also given for both of them. We know the RPM for the pinion. We know the diametral pitch, which is 10 teeth per inch. And the face width, which is usually the same for both, is 1.5. The modulus of elasticity and the Poisson's ratio for both were also given. We have a 4 horsepower to be transmitted through this gear system. We have a quality of a commercial quality gearing of a QV equals to 6. And we were given some other information that I'm going to discuss later. So we started by calculating the pitch diameter for the gear and the pitch diameter for the pinion. And then using the diameter of the pinion, okay, we calculated the pitch line velocity. Now, the pitch line velocity, ya shabab, we calculated it using the diameter of the pinion. But indeed, you can calculate it. It's supposed to be the same as the pitch line velocity if you calculate it using the gear. So you may ask me a question, how? The diameter of the gear is 5.2 while the diameter of the pinion is 1.7. So how comes I'm going to get the same velocity? Well, don't forget that the number, the RPM for the gear will be different. So in the end, this one will increase, that one will decrease, and you will end up having exactly the same pitch line velocity. This is the velocity that when the two gear match, they will move with it at the same time. So that velocity is the same. Now, which means if I have the same pitch line velocity, I can go use this equation, okay, which is WT. So from these, I get the pitch line velocity. From the pitch line velocity, I can calculate the, the transmitted load, which is 4 horsepower, and then the pitch line velocity, which is 801.1 feet per minute. Then if I would have to write the equation, okay, for sigma, so sigma is equal to WT multiplied by then KO, KV, KS, and then the diametral pitch divided by F, and then Km multiplied by Kb and divided by J. So if you look at this, we just found our first unknown, which is WT. Correct? And then we start chipping these constant one by one. KO is the what, ya shabab? Is the what was it called? Was the load factor? Uh, and let me just get the right name for it. I don't want to. KO is the overload factor or the application factor or the surface factor. And since it was said in the problem that this operation is smooth, then we should assume it to be 1. Okay, otherwise you will be told, is this a light shock, a medium, an intermediate, or a high or heavy shock? Then we will move to KV. KV is the dynamic factor. The dynamic factor depends on the quality of the gear. So if the quality of the gear is given, which is 6, quality number, then we can substitute QV over here to calculate a constant B, and then this constant B can be used to calculate another constant A, and then this A is used in this equation along with the velocity, the pitch line velocity, in order to get KV. So KV is known. Now, I'm going to make this analogy very clear from the beginning for you over here. Okay? What is WT? WT is the transmitted load. If the pinion pushes against the gear with this load, the gear will push against the pinion with the opposite way, but the same magnitude. So that's why WT is the same for the pinion and for the gear. KO should be the same for the pinion and the gear. If it is smooth, it's smooth for both of them. KV, if you look carefully at KV, the quality number usually, it's a quality number for both. So, and the pitch line velocity is supposed to be the same for both, which means both the gear and the pinion will have the same KV. Okay? So, then we move to KS. So, remember with me, PD is the diametral pitch, which is the same for both the pinion and the gear. F is the face width, which is the same for both the pinion and the gear. Now, J is a factor which, if you remember, has a curve like this. You remember that? Something like that. And I told you that if you know the number of teeth for the pinion, and these curves are for the mating teeth, then you should be able to know what is J for the pinion. And if you know the number of teeth for the gear and the one for the pinion, the mating gear is going to be the pinion, you will have another J. But these two J's were given to us in the question, but if they were not, then you can find them from the curve. So this J is known, this F is known, this PD is known. What we are left with, ya shabab, is KS, KM, and KB. KB from the end, this is the rim factor. And in the question, nothing was mentioned about the size of the rim. So KM will be equals to 1. Now, just to tell you, ya shabab, the book solved the problem in a systematic way, which I would not advise you to do if you are solving a quiz or a homework or exam and so on. Why? Because in reality, you should first write the equation for sigma, and then the equation, let me write it down for you, for SH, which is equal to ST multiplied by YN, then this is divided by KT multiplied by KR, and then all of this is divided by sigma. That's sigma over here. So if you think about it, if you want to be ready to solve these two equations for both the bending and the factor of safety, then you don't only need to find KO, KV, KS, KM, and KB. In addition to that, you need to find YN, you need to find KT, and you need to find KR. And finally, you need to find ST, which is the strength. You do the same with the wear. Okay? Now, the wear equation, if I would have to write it for you, the wear equation, sigma C is equal to CP, that's a new constant, so you need to find CP, multiplied by WT, KO, kV, ks, then km divided by dp multiplied by f multiplied by cf divided by I under the square root. Now, if you look carefully, if I compare Wt, I know it, it's the same. Ko, I know it. Kv, I know it. If I know Ks from the bending equation, I will use the same Ks for the weir equation. And then if I calculate Km from here, I will use it also there. Yeah? Now, dP is something very interesting. The equation for the contact is originally in the as a function of the pitch, the pitch diameter for the for what? For the pinion. Okay? And for that, you need to be very careful. It's always the same. Whether it is the pinion or the gear, you will still use dP. Okay? Now, uh, what happened? Then we have F, which is the face width, and CF, it is the surface factor, which we are going to talk about later, and I. So you need to find I, you need to find J. This is something you need to do. Now, if you write down these equations, then it will look so easy for you to just go and calculate those coefficients that you need. So let me tell you, just I need to check one thing over here. Yeah, all right. Okay, understood. So we just found Ks. What is our job now is to find Km, is to find I, and to find CP, and so on. So I hope you remember these equations very well. The next step, just to remind you, was to find Ks. Now, Ks as an equation, it is equal to 1.192 multiplied by the face width multiplied by the square root of y divided by the diametral pitch to the power 0.0535. Now, the F is the face width. No difficult, you know, it's easy. And this one is the diametral pitch, which is given. Y is a value that we calculated by knowing the number of teeth, and then we get Y. So we were lucky that for 17, Y was 0.303. But we did not find it. We found Y for 50 and for 60 and for 40 or something like that. So in order to find Y for 52, we need to interpolate. After interpolation, it turns out that this Y is 0.412, and that's how we found Ks for both the gear and for the pinion. Okay? Now, the next step is to find Km. Now, for Km, ya akhwan, if you recall, it is a bit of a demanding factor. So Km, in order to find Km, we need first to know, is the tooth or all of the teeth are crowned or not? So they are uncrowned, so CMC is equals to 1. And then we have another equation which says that CPF equals to F divided by 10 multiplied by dP plus a constant minus some constant multiplied by F. This is for the range when F is greater than 1 and less than something. So 1.5, a face width of 1.5 fall between this category. And if that's the case, the only thing we need to worry about is F divided by 10B. Why? Because this must be not less than 0.05. If it is less than 0.05, then we should substitute it as 0.05. We finish from this, then we go to the idea of the distribution, in the sense that if we have the two bearings far away, and then this is the shaft. Now, the if the gear is not sitting on the mid span, this is the mid span, okay, and the gear is sitting right there, then the distance over here, which is called S1 divided by S, is going to determine what is the value of CPM. Now, CPM, it is common to say, if you say the word the two bearing are adjacent, it means that, just as an exaggeration, that probably one bearing is here, the other one is here, and this is the shaft. Now, I want to tell you one thing. If the center line, the midspan, is here, I mean, what are the chances? What are the chances that the gear is here? I mean, Shabab, even if you try to do that, physically it's not possible. The gear has a width, so most likely, the gear will be much closer to the midspan than what you think. So probably it's going to be either on the midspan or not. Now, which means that this distance divided by this is very small, particularly less than. So S2, S1 over S is less than 0.175. If that's the case, then CPM is equals to 1. Now, either you hear the word or you read it, I mean, which says that they are adjacent, and which means that this is the condition we have, or you are given the dimension and you can calculate the distance from the midspan to one of the bearings, and then divide it by the entire span between the two bearings and see if the ratio is less than 0.175 or not. If it is, then you should use CPM as 1. If not, then you should use some other value. Now, the last one is, or the one before the last one, is about the unit. Is it enclosed? Is it open? So this is an enclosed gear unit, and for that, the CMA is with a for a given face width, because there is an equation and there is a curve. So if you look at the curve for the enclosed commercial unit, and you know that F is equal to 1.5, you should be able to calculate CMA. The last one is CE, which is related to any adjustment or modification, and it is 1 since there is nothing mentioned like that. So what did we get? We got KM finally. Okay. Now, we got Km, we are done with sigma. Now we need to find the parameter for the factor of safety and the parameter for the contact. Now, the first one is Yn. Now, Yn, ya shabab, is similar to Zn, but you need to be very careful in one aspect. Now, Yn, we need to find it for the pinion. Yn, we need to find it for the gear. And then Zn, we need to find it for the pinion. Okay. And Zn, we need to find it for the gear. What are these curves? They are for life or cycles correction. We were mandated to calculate the life based on 10 to the power 8, but the strength, all parameters, mostly strength, is determined based on 10 to the power 7 and 99% reliability. So the reliability is different and the life is also different. Now, there are curves for Yn, each one having a single equation with it. But the book was cooperative, and in this problem, the book gave us the equation. That equation, Yn, is actually like this, which is equal to some constant A multiplied by n to the power a constant B, which is A is 1.3558 and B is minus 0.0178. By the way, I just made up A and B. They are not in the book, just to explain things easier. Now, for the gear, يا شباب, the gear, if the pinion rotate 10 to the power 8 or make 10 to the power 8 cycles, the gear will more likely, since it is bigger, will make smaller cycles. So the life, if I put the constant A, then the life here is supposed to be 10 to the power 8 divided by mg, and then I raise to the power b. What is mg? Is the gear ratio or the speed ratio or something. mg is n for the gear, which is 52, divided by n for the pinion, which is 17. So you need to divide by that. The difference, look, here we are dividing by it, and then we got yn a little bit different, but you need to show that you understand this very carefully. Now, you can do the same. The equation for Zn is given to us, which is almost the same with what? Let's call it A prime and then n to the power B prime. What is A prime, B prime? It's over here. It is A prime is actually, which again I made it up, is 1.4488. What is B prime? It is minus 0.023. Again, for the pinion, Zn for the pinion is 10 to the power 8, while n for the gear is 10 to the power 8 divided by 3.059. Remember, this yn is for bending and Zn is for contact or wear. So two corrections, each one for each mode of failure, which is bending or contact. Now, the next part is the reliability. The reliability, we have been told it's 0.9. So we have a table which says that if this is the reliability and it is 0.9, then Kr should be equals to 0.85. That's very easy. The next one is I. I is equal to sine phi t cosine phi t divided by twice m capital N. All of this is multiplied by mg divided by mg plus 1. mg is the gear ratio, which is the same as 3.059. That's very easy. Phi here is the pressure angle, so it is 20 and 20 for spur gear, right? Mn is the loading, the load sharing factor. For spur gear, it's equal to 1. For helical gear, it's a hell of a story. So we're going to see that in another occasion. I mean, next example. So this is the I. And now, look, we go and we look at the material. This is a grade 1 steel. We have been given the hardness for the pinion as well as the hardness for the gear. So I go to the table, for example, figure 14.2, and then I will see a curve for grade 1 and a curve for grade 2. So for grade 1, all what I need to do is to look for hardness of 200, and then I get ST for the gear. And then I go for hardness for 240, and then I get ST for the pinion. And this is exactly what we did. But the book decided to use the equation. The equation for these curve are given either in the figure or in the caption. So the equation here is 77.3 multiplied by 240, which is the hardness for the pinion, plus 12,800, which is going to give you this much of strength for the pinion and this much strength for the gear. This is not the end. We need to find the same strength for the contact or for the wear. We go for the wear table or figure, it's 14.5, and we do the same. It is function of the hardness, and there you go, you got the strength. Okay. Now, with respect to wear, we know that hardness makes a rule. So we have a factor which is called CH that is only applied at the gear, not on the pinion. It's assumed to be 1 for the pinion. Now, that factor we need to do first, take the hardness, the Brinell hardness for the pinion divided by the Brinell hardness for the gear. And this, if you recall, this is supposed to be less than 1.7, greater than 1.2, which we got lucky and got it 1.2. If that's the case, then we will calculate A using this equation, then substitute this A in here to get CH. That's it. Okay, now we move on and look at this. Now I want to show you. This is sigma for the pinion, the bending stress for the pinion. What is it? It's equals to WT. WT is here. There it is. And then we have K0, which is 1. And then we have KV, which we calculated as 1.377. All right? Later, we have KS. Now, KS, I'm going to circle it in green. Why? Because KS is different. KS depends on the number of teeth. The Lewis factor Y is different, and that's why KS for the gear is different than KS for the pinion. Similarly, the book in the question told us about J, and J for the pinion is different than J for the gear. So the remaining factors are the same. This is the diametral pitch, 10. This is the face width. 1.22 is what, ya shabab? Is km. I mean, the fact that this is a crown, not crowned, is it in the span, is not, these are mostly applicable on both. So here we got the sigma for the pinion. If you want to find the factor of safety for the pinion, then you go and take the strength ST for the pinion. Then you take Yn for the pinion, and then you divide this by the temperature factor, which is 1, multiplied by Kr, which is 0.85. And then you divide it by sigma for the pinion. There it is. So what did you get? You get 5.62. Now look, I want you to compare, and you will see that this number is different because KS are different, and this number is different. The remaining numbers are exactly the same for the gear. And for that, when we get the stress of the gear, this is how much it is. Now be careful. ST is different for the pinion than for the gear. Yn is different for the pinion than for the gear. The reliability and the temperature applies on both, and then the stress is from here. You should not use the stress for the pinion to calculate the factor of safety for the gear. So how much did we get? We get 6.882, while this one is 5.62. So the pinion is still in more risk than the gear. Now let's move on to the wear. Okay, now for the wear, the equation start with CP. Now CP, I mean, let me mark it with red, since red here means the same. CP is 2,300 square root of PSI, and it is the same because it's calculated based on the modulus of elasticity and the Poisson ratio of both the gear and the pinion. Okay, WT is the same, right? K0 is the same as what we did before. KV is the same, but I am here gonna use KS in green over there for the pinion. What is KM? KM is the same for both. What is CF? CF is the same. We don't have actually a quantification measure or way to know what is CF. Now, what is DP? Is the diameter of the pinion. We are measuring CE, sigma C for the pinion, but the equation says it is always the diameter of the pinion. So it is always the same. And then F, so this is CDP. This is the face width, and this is I. I is also the same. Why? Because I is equals to sine phi cosine phi, both the same, divided by 2mn, and then mg divided by mg plus 1. Do you see anything here which is different for the pinion than for the gear? No. So it is also the same. So we ended up with only one green circle, which is KS. So what did we do here? Look, we calculated the sigma, the stress for the contact. Okay, and then we went ahead and to find the uh, the factor of safety for the pinion. Now in here you need to be very careful. Sigma C or SC is different for the pinion than for the gear. Zn is different for the pinion than for the gear, while 1 and 1.85 are the same. So what is sigma C? It's this one. So it is different for the pinion than for the gear. Okay. And there we go. What did we get? We got the factor of safety. Okay. Now, in the book, what is it saying? It says here that if you want to find sigma C for the gear, okay, since the only difference is KS, then basically, if you take KS for the gear and you divide by KS for the pinion, and then you raise this to the power half, and you multiply this by sigma C for the pinion. Do you know what did we do? We're saying we are doing the same here, but in order to cancel KS for the pinion, we divide by KS for the pinion, and we multiplied by KS for the gear. But don't forget that this is under the square root. So if you do this, and you multiply it by this value, which is sigma C for the pinion, you will find it for the gear. You understand? And that's basically what did we do. Okay. So what happened later? We know that you have to include for the gear. Let me show you this. This is very important. Okay. This specification is different. So basically, let me open, ya shabab, just give me 1 second. I need to write down the equation carefully, making sure it is absolutely right. Okay, so what do I want to write over here? That SH for the pinion, okay, is equal to SC ZN, okay, divided by KT multiplied by KR. and this is divided by sigma c. This one is for the pinion. What is the difference between a pinion and a gear? Is that SH for the gear, okay, is equal to SC for the gear, ZN for the gear, but you need to multiply CH. That's the difference, because CH is only applied on the gear. And then you divide this by KT, KR, okay? And then you divide this by sigma C, and this one become for the gear, okay? So if you look over here, CH was 1.05, so there we go. We have to add it in. Then we put this for SC for the gear, and this one is ZN for the gear. The sigma is for the gear, and then we get the factor of safety. Okay. You can do the same for the pinion, of course. Now, what do I want? I mean, we have like 10 minutes. So in this 10 minutes, I have to see if I can cover as much as possible out of this problem. Now, this problem, ya shabab, is nearly identical to the other one, okay? Except that somebody decided to use helical gear instead of spur gear. So the question here in your mind, out of everything I did, what is going to be the same? What is going to be different? Okay? So, first of all, look, the pinion, and this is the gear, okay? The number of teeth is still 17, it is still 52. The diametral pitch, okay? The diametral pitch is 10, okay? Horsepower is 4. The pinion rotates with RPM of 1,800 revolution per minute. Okay, the face width is 1.5, face width is 1.5. The difference is that we have been told that phi n, the normal pitch angle, is 20 and the helix angle is 30. You see that? The other information, like the quality is 6, the bearing are immediately adjacent. The Brenel hardness is 240 and 200. The reliability is 0.9. The pinion has a life of 10 to the power 8. Everything seems to be the same. The gear, everything is running smooth. So let's see, where are we going to treat things differently? Okay, so if you go here, I think I went twice. Okay, so if you go here, ya shabab, it tells you that, first of all, KO is the same. By changing the gear from helical to spur, doesn't mean that you introduced or you removed something in terms of shock or others. This is part of the operation. The gear is forced into it. It's not the reason. The gear is not the reason. So K0 is 1. It will stay as 1. Okay? Then YP, you remember Y? Which was 0.303. The lowest factor will still be the same. Why? It is dependent on the number of teeth. The number of teeth did not change because I changed the gear into a helical gear. So YP is 0.303. What is Y gear? Well, I can go and interpolate for 52 teeth and I will find it to be the same, 0.412. All right. Now, what is mg? Ya shabab, mg is ng divided by np, which is 52 divided by 17, which is the same as before. 3.59. Okay, so if the Ks equation is 1.19 and then I have the face divided by the pitch diameter multiplied by the square root of y to the power 0 point something something. This is the same, this is the same, this is the same. So Ks for the pinion is the same, Ks for the gear is the same. You see that? Makes sense. Now, what is Yn for the pinion? What is Yn for the gear? What is Zn for the pinion? What is Zn for the gear? They are all dependent on the number of cycles for the pinion, which is 10 to the power 8, and the number of cycles for the gear divided by mg. These two are the same. And if in the question we are asked to use the same equation for life, then these factor, all of them will stay the same. Is that good? So look, Yn for the gear, Yn for the pinion, Zn for the pinion, Zn for the gear, they are still the same. What is Kr? The reliability factor. The reliability يا شباب depends on the factor. The reliability factor depends on the reliability. If I need 0.9, it is the same. Should I use spur gear or should I use helical gear? It's the same. It wasn't given to us as a function of the gear type, so it's still the same. Kr is still the same. Kt, the temperature, still the same. Cf is still the same. Cp, still the same. I didn't change the modulus. I didn't change the Poisson's ratio. So Cp is still the same. Also, since the Brinell hardness for the pinion is the same as before, 240, and the Brinell hardness for the gear is 200, and I am still using steel grade 1, then S, T, S, C are also the same. So what is different then? Well, let's dive into it. Number one, if you have a helical gear, the pitch diameter, so the diameter of the pinion is equal to the number of teeth for the pinion, which is 17, divided by the transverse diametral pitch. We have a transfer, we have normal. The one which is 10 that was given to us is actually the normal. So I need to find the transverse diametral pitch. It is not 10, it is 10 multiplied by cosine 30, which is the helix angle. So I got, this is 8.66, not 10 like before. And if it is 8.66, when I divide 17 by this, I will get a different diameter. A pitch diameter will be different. If the pitch diameter is different, then the pitch line velocity is different. And if the pitch line velocity is different, then the transmitted load is different. Is that right? And if the velocity is different, remember, A will still be the same because the quality number QV is 6. But KV is not going to be the same because the velocity here is different. It was 8.01. Here, it is 925. So KV is different. Not only this, ya shabab, I, which is equal to sine phi t cosine phi t, and so on and so on, actually I has too much problems. It is divided by 2mn. We were very happy when we told you that mn for spur gear is 1, but mn for helical gear is an entire story by itself. So this angle phi t is actually the tan inverse of tan phi n divided by cosine psi. What is this? 20. What is this? 30. So this angle is not 22 like a helical gear. It's actually 20. It's not a 20 like helical gear. It's actually 22.8 degrees. Now, what is MN? Well, I'm gonna remind you what is MN and then I will stop. MN, yeah, Shabab, this is the last thing I'm gonna say and then I'm gonna let you go. So M capital N, the load sharing factor or ratio, it is equals to P capital N divided by 0.95 Z. The P capital N has its own calculation and the Z has its own calculation. We're going to continue this later. Okay, Shabab? I'm not going to take the attendance today, so I wish you an enjoyable weekend, inshallah.